Hi, and welcome. This is the fifth podcast in Unit 4 on solutions chemistry. And one of the reactions that we learned about in the last podcast was a reaction called a redox reaction. And we learned and got some practice with assigning oxidation states. And now what we're going to do is we're going to take it one step further, and we're going to look at more complex redox reactions. And we're going to do what we just did, so balance the redox species within the reaction, but then go on to actually balance the full-on chemical equation. And we call that the half reaction method. This is sequential, and ultimately you're going to master this process by practicing it. Now, hopefully assigning oxidation states wasn't difficult. We're going to apply that and go a step further. I'm going to do exercise 19 in our notes right now. And then I'm going to leave exercise 20 for us to do in class or on your own. Now, here are the 9 steps that you're going to follow. We're going to go one step at a time. And my exercise 19 box kind of cut off, plus it's a really small box to do this work in. So I'm going to come back up here to the top of the page and, kind of work this problem out with my tablet and my pen here. We're going to follow those steps in the page above. All right, so what we have here, you guys, and if you go to exercise 19, they have a description of what's going on. And they're saying that potassium dichromate, and just so you know, potassium dichromate is essentially, this is the chromate ion. You'll notice that potassium is not in this reaction, and that's because it's essentially a spectator ion. What we have here is potassium dichromate is a bright orange compound that can be reduced to a blue-violet solution of chromate 3+ ions. Under certain conditions, potassium chromate will react with ethyl alcohol, and I'm going to highlight alcohol right now. Ethyl alcohol is that species, and it says here is the following reaction. We're simply going to balance this redox reaction. Now, you're going to do this in steps, and so the first thing that you need to do is go up to step 1 and read it. And what you're going to do is divide the equation into its oxidation reaction and its reduction reaction. Now, in order to do this, you need to, again, there's that mnemonic, oil rig. Oxidize is to lose, reduction is to gain, electrons that is. And so if we go down here, I'm going to scroll out, come out a little bit here. We're going to take this entire reaction and decide which species are being oxidized, which ones are being reduced, and write those into 2 separate reactions, hence half reaction. Now, the way that we do this is we need to assign oxidation states to each of the species in the reaction. And we actually spent the last podcast learning how to do that. So let's go ahead and do a quick review. Now, starting from left to right, hydrogen, you guys see that it is an ion. So its oxidation state is going to be its charge, a +1. And you're going to go ahead and skip on over here to the chromate ion. You will see that it has an oxidation state of a 2- or -2. And what that means is that when I figure out the charges of everything, I need to have a 2- remaining. So go back up to the oxidation rules and how you assign charges if you forgot this. You should remember that each oxygen has a -2, and since there are 7 of them, this side of the molecule is sitting in at a -14, -14. Now, it is from this oxygen that's going to allow me to determine the charge of these chromium atoms. You can see that there are 2 of them. Remember, this species has to have an overall charge of a 2-. So what does the charge of each chromium atom have to be in order for us to have a 2- remaining? That's right, it has to be +6. And since there are 2 of them, that would give us a +12. And +12 - 14 is a -2. Okay, all right. So up above the element, I'm going to then write the oxidation state of each thing. So that way we can kind of separate that from our thinking down below. All right, moving on. Now this one's interesting. You see here this ethyl alcohol molecule is C2H5OH. And some of you might want to combine those 2 hydrogens, but in this case, it's very clear that how it is written is going to allow us to determine its oxidation charges for each element. Now you'll notice it's a neutral element, so the charges should balance out to 0. And one of the things that was told to you, and this is important, is this hydrogen here. When hydrogen is bound to other nonmetals, and you can clearly see that oxygen, hydrogen, and carbon are nonmetals, it's going to take on a charge of a +1. Okay, you know that oxygen is a -2. You know that these hydrogens here, this H5 component, they're each they're each +1. And since there's 5 of them, your total would be a +5. Okay, you with me? Now, listen, if you add up the charges that we have so far, so I'm going to kind of come down here a little bit more. You have this +5 and this +1 and this -2. You're going to get a +4. So if all of those charges, the hydrogens, oxygen, and the other hydrogen, add up to a +4, then what must the charge of each carbon be to get this compound to balance out the charge of 0? That's right. It's got to be a -2. And since there's 2 of them, that would give us a -4. And you can see that -4 + 4 is 0. So up above, let's go ahead and write the oxidation states of each thing individually. This would be a -2. This would be a +1. This would be a -2. This would be a +1. Okay, so we're getting there. The other side's a little bit easier. If you look at the product side, this seems to be a little bit more straightforward. The oxidation state of this chromium 3+, well, it's +3. It's 3+. That's the charge of it. That's its oxidation state. The CO2 molecule, you know that each oxygen is -2. There's 2 of them for a -4. So this one should be a +4. And then water, you can see that each water molecule is -2. So each of these have to be a +1. Okay. So hopefully you're getting, hopefully you're getting a little bit more practice here on how to apply oxidation charges. Now, from these charges, you can now determine which species in the reactant, so on the left side, is being reduced and which one is being oxidized. And that's going to allow you to set up your half reactions. So if you look at the reactants, one of the big thing that stands out to me is when I look at this chromate +6, and then I go over here to the product side after the reaction has occurred, did it gain or lose electrons, you guys? Did it gain or lose? You go from a +6 to a -3. Again, you might want to write the mnemonic device oil rig to keep it fresh in your head. Well, it certainly looks like this one gained a negative charge. So it looks like this was reduced. So one of my half reactions is Cr2O72- yields Cr3+. Okay, that's one of the half reactions. Okay, so if you look at now, we need to figure out what species is being oxidized. So in other words, which species is losing electrons. I'm quickly going to just point out here that if I look at my hydrogens, its oxidation state on one side is a +1, and I come over here to my right side and I also see the hydrogen is a +1. Another good example would be to draw your attention to the oxygen here. This oxygen that I just circled has a -2, and if I come over here, it's a -2. And when these numbers are the same, that means that neither oxidation or reduction is occurring. Okay, and for space reasons, I'm not going to include the state of matter, you guys. I'm just going to go ahead and skip that for now to make this a little bit cleaner on the board. All right, I know that seems like a lot, but that was the first step. So apply oxidation state rules, figure out what species was oxidized, which species reduced, and separate those reactions, okay? The next thing you're going to do is balance all the elements besides hydrogen and oxygen. So what that means is every element that is not a hydrogen or oxygen, make sure there are the same number of elements on both sides. Let's go over here to the half reaction on the left, the one that was reduced. And I see there is 2 chromium here, and there is only 1 over here. So I would put a 2 coefficient on this side of the equation, and it looks like every element is balanced, but it did not want us to balance hydrogen or oxygen. So I know you see an oxygen here and you're wondering, where is it on this side? We're going to balance that in just a second. You guys, this line is kind of separating the 2 half reactions so you can distinctively see it. Okay, so everything looks balanced on that left side. Now, what does it say? Let's go ahead and do the same thing to the other reaction. put me on pause and you balance. So remember, you're balancing every element except for hydrogen and oxygen. So there you have it. I put a 2 coefficient. Third step, we're now going to do the oxygens, you guys, and we're going to do this by adding waters, H2Os, to the appropriate side of the equation. So I'm going to rewrite this, you guys, so you can see all the steps. So I've got chromium, and I've got 2 chromium ions over here, and I'm going to add, in order to get it to balance to 7 oxygen on the right side, I'm going to add 7 water molecules. You can see that 7 times 1 is 7, so therefore I would have 7 oxygens over there. Okay, let's go ahead and do the same thing to the other half reaction. Let's balance the oxygens. So can you put me on pause? And remember, you're going to add water to the side that needs it. So I have a total of 4 oxygen on the product side. So I think the best thing for me, since there's already 1 here, would be to put 3 water molecules. Then you'll have that ethyl alcohol molecule. And then you've got your product. Now we're going to balance the hydrogens. And we're simply going to add hydrogen protons to the sides of the reaction that we need to balance the number of hydrogens. So let's start to the left over here. And I notice that there is 14 hydrogens over here on the product side. So to make up for that, I simply add 14 hydrogen protons to the left side because they have to have the same numbers. So you'd say 14 hydrogens, H plus is what you would write. Then write the other product, or excuse me, the other reactant. Write the whole reaction rather. Okay, let's go ahead and do it to the other side. So let's go to the other side of the reaction. We need to balance the hydrogens. Remember, we're going to add hydrogen protons to the correct side of the reaction that needs to balance them. Reactant side looks like 12 hydrogens on the left side. So I'm going to simply counteract that by adding 12 hydrogens to the right side. Okay. And then just go ahead and bring everything down and write it. Okay, so if you look, I've balanced both equations using hydrogen protons. So at this point, we've done the first 4 steps. We're getting there, you guys. It'll get quicker and quicker. The 5th step is you're going to balance the charges by adding electrons. So in redox reactions, we're going to actually balance everything in the reaction, including the charge. Don't forget the coefficient, because you're trying to count how many electrons there are. So when you get to this step, you need to concern yourself with the coefficient and the charge. So in this case, it's a plus 14. Come on over here. This is just a 1 coefficient, and you're going to see that it's just, a minus 2. Do the same thing to this side. So you're going to get a plus 6. And then this actually, water will balance out to 0. So 7 times 0 will be 0. You will see that indeed you're going to need to add electrons to which side of the equation. Okay, so one of the things that you can easily do right here is you want these numbers to be the same. Okay, you want the charges to be equal, the electron count on both sides to be an equal number. So if you look at this side that has plus 12, and I go ahead and add, so I'm going to rewrite the entire equation. If I add 6 electrons to this side, in addition to the 4 hydrogen protons, again, we're just rewriting everything here. And let's do the same thing over here on this side. Now, you got to get practice at this. Water will have an oxidation state. These will balance out to 0, so 3 times 0 is 0. But you can see there's no charge here, so this will be add up to 0. Again, this is 0. 2 times 0 is 0. And so the only charge we have here is 12 positive charges. So you have 0 is to 12 positive charges. So, excuse me. Which side are you going to add electrons on to get these numbers to be 0? Well, you're going to have to add electrons onto the product side. Okay, there you have it. You have now balanced the charges of each half reaction. Now, the last couple of steps of this process, which is very important, is you're going to recombine these 2 reactions again. There's one reaction, and the other one, I'm going to align the arrows and do the second reaction, the other half reaction, and write it directly below. Okay, so take a look. We have the two reactions stacked on top of each other. And now what we're going to do is we're going to make sure that the electrons are equal from both half reactions. And you can see, I'm going to go ahead and highlight the electrons for each reaction. We have 6 in the reaction that was being reduced, and we had 12 over here in the reaction that was being oxidized. These have to be equal. So the only way we can do that is if I take a 2 coefficient to the first reaction and multiply this 2 by 6, which will give me my 12. Well, don't forget the distributive property is going to apply here. And don't forget, you're going to need to distribute that 2 to every other coefficient in the entire reaction. And so down below, let's go ahead, and I'm actually running out of space because I'm writing big. I'm going to go ahead and rewrite this balanced reaction after we distribute that 2 right below it. There's the first one. Now I didn't make any changes to the second one, but again, I'm still going to rewrite everything here, you guys. Okay, notice how I try to keep the arrows lined up to help me keep my reactants distinct from my products and kind of clean it up. For example, I have 12 electrons on the left side or the reactant side of the reaction. I also have 12 electrons on the right side. And so these are going to cancel out. Okay, now let's look and see what other species will help like kind of cancel out here. You'll notice I have 28 hydrogen here and 12 hydrogen over there. Now what ends up happening is that cancels out my hydrogen completely, but reduces this to 16. I have 16 left over on this side. Let's see, what else can I balance here? Oh, I can balance water. I have, let me go ahead and highlight this in another color. I have 3 waters right here on this side, and I have 14 waters on that side. And so what would happen is I would consume all 3 of these water molecules and have 11 remaining over here. So after I have cross-canceled essentially everything that I can, I'm going to put a line and rewrite the entire reaction in one complete reaction. In other words, everything on the left side of the arrow, my reactants, which will be 2Cr2O4 2-, and then the other thing I have here is 16 hydrogen. Don't forget to write that. And then you have this ethyl alcohol. Okay, and then let's go ahead and write everything that is on the product side from both of the reactions. And that is this. You got, don't forget your water, 11 molecules of it, and 2 CO2. And that, darlings, is how we balance a redox reaction. I will be honest, that one was a little bit more complex than what you'd see on the AP exam. We'll go ahead and try exercise 20 in class, or you can try it right now and we can follow up in class. Thank you so much.